Well, let's hear it. Good morning, everybody. Welcome. Good to see you all. Yeah, we're trying to finish up chapter 10 today. I may or may not get there. We got David over on the left here. Anything to report so far? We're good. Good for now. If you want to type anything in there in real time, David's got the mic, or you can just yell at me. Hey, remember that fractional bonus point or whatever? It's just like something up to 1% that I'll add before I do the rounding. Now, keep in mind, I am only able to submit an integer to the acorn at the end of the course, so I'm going to have to round. But I guess, 0.5s round up, 0.49 or whatever goes down. So yeah, so right now everyone's getting a bonus of 0.18 because 18% of you have already done your course evaluation. So you have until December the 9th to find it. Some people have found an email. I don't know, has anyone ever seen an email from course.evaluations at UToronto? I did, but I got it just a link to this response rate thing, and some of you have gotten that email. Another place to find it is when you open up your computer and see the Corcus, q.utoronto.ca. It's outside the course structure, way on the left. There's a bunch of links, and somewhere near the bottom it says course evals. You'll see that all your courses request this. And it is, like I say, I've been to a few different universities. University of Toronto really takes these course evaluations very seriously. And they're somewhat controversial a little bit because some people think that students are biased and stuff like that. But for good or for bad, they get used in promotion through the ranks, tenure decisions, that kind of stuff. So what you say really can have an impact on your professors' careers. Although I've already got tenure, so may not be able to get me fired, but I guess Roya is not. So, oh yeah, we're going to do this, the pogo stick thing. Try to figure out the mass. I was going to do an example for this, and I forgot to, or I sort of ran out of time last time. Want to do it? Are we okay for thingy so far? Yeah, there's a little video of it actually happening, but idea is there's some spring with a spring constant, and it's a pogo stick made of metal, and it has some vibrational period when it's empty. But when you put a mass on there, the vibrational period decreases somehow, of course, according to our simple harmonic motion equation, which we had in chapter 10. So I'm just going to use that equation. The body mass measurement device chair, mass 32 kilograms, has a vibrational period of 1.2 seconds when empty. When an astronaut sits on the chair, the period changes to 2.1 seconds. Determine the mass of the astronaut. So in this case, the mass of the chair, we'll call it 32 kg, and the time period for just the chair only is 1.2 seconds. And we'll say the chair plus the astronaut, CA, I guess, is 2.1 seconds. I'm just listing my unknowns here. I am trying to find MA, the mass of the astronaut, question mark. So I might try to do this as two systems. I love defining systems because that's what they do. Maybe the chair plus the spring of some spring constant K. So there's like the wall, the side of the space station, and the space station has some very, very large mass, so it doesn't move very much. And then a spring with some spring constant K, which we don't know, unfortunately, but maybe we don't need it. And the mass of the chair, it's going to oscillate back and forth with some Tc. And then the second system, not two segments, but just two different things, I guess, that are going on, is the chair plus the spring plus the astronaut. And that's what changes the period, because the mass is different. Whoop, astronaut. Okay, and then you've got same sort of thing, same K, but now we've got the mass of the astronaut plus the mass of the chair, all kind of attached. And now it goes back and forth with this TCA. Okay, and the same wall over here. So let's use equation, it's called 10.7. In your e-text, I found it on page 294, but this is something that should be on your aid sheet. It looks like this, 2 pi square root m over k. It's the period for simple harmonic motion whenever you have a mass on a spring. You've got the mass and spring constant in newtons per meter or something. So I think my strategy here is I'm going to use system 1 to solve for k. Because I know that period and I know the mass. And then use system 2 to solve for mass of the astronaut. So that's kind of my second step is building up a strategy in my head of what I'm going to do to solve this problem. Then I do the math, and then I plug in the numbers. So system 1 is that t, this is just the chair alone, 2 pi over the mass of the chair divided by k. So I can square both sides. I got tc squared over 4 pi squared is equal to the mass of the chair divided by k. And I can solve for k. K is equal to 4 times pi squared times mc divided by tc squared. And for system 2, I've got this new thing I know, 2.1 seconds, is 2 pi times the mass of the astronaut plus the mass of the chair, all divided by k. And same sort of thing, I don't like square roots, so I'm going to square both sides. Over 4 pi squared is equal to mass of the chair plus the mass of the astronaut divided by k. So I can kind of solve it out. I've got mass of the chair plus the mass of the astronaut is equal to k over 4 pi squared times tca squared. Well, so I can actually solve this for k over 4 pi squared just to save myself some steps. It's mc over tc squared. If I take that now, sort of green, take this thingy and go and plug it into here, I can say that mc plus ma is equal to mc over tc squared times tca squared, I think. So the mass of the astronaut is equal to mc tca squared over tc squared minus mc. So it's the mass of the chair, and I can just sort of take all this stuff out. tca over tc squared minus 1. So I get 32 kilograms times 2.1 over 1.2 squared minus 1. I got 66 kilograms, something like that. I don't know, there's a few different ways of doing that algebra, but hopefully you end up with 66 kilograms. Was that the only thing? Oh yeah, the other thing I was going to do is talk about the energy. I think there was one learning catalytics question we didn't get to last time, so I want to do it now. We're talking about energy of simple harmonic motion, and it was stored two ways. There's either just kinetic energy of the mass on the spring, so the mass has some speed v, and the kinetic energy is 1/2 mv squared. And then the other place you can have energy stored is the potential energy in the spring, which is 1/2 kx squared, where x is 0 at the equilibrium, the center of the simple harmonic motion, but then it gets negative or positive as the thing oscillates back and forth. So when you're at your maximum x, or minimum x, that is when the mass momentarily stops. So x equals a or x equals negative a, then V is 0, so the energy, which is constant actually, is just equal to 1/2 Ka squared. Or, conversely, when it's passing through equilibrium, x equals 0 for a moment, and that's when it has its maximum speed. So you have 1/2 mv max squared. So these two things are oscillating, v and x, but at these two particular times, all of the energy is either in kinetic or in potential of the spring, and you can use either one depending what's convenient to get the total energy. When the mass of the card is large, it moves slowly. So this is another, you can solve this out for Vmax in terms of amplitude. If the spring is stiff, the cart moves more rapidly. And we're not doing damping yet. We're going to do damping in about 10 minutes. A ball of mass m oscillates on a spring with spring constant k is 200 newtons per meter. The ball's position in meters is x equals 0.35 meters times cosine 15t, where t is in seconds. So what is the total mechanical energy of the ball plus spring system? By the way, 15 is in radians per second as well, because you're supposed to use radians mode in your calculator here. But I'll give you a minute to try to compute this. Maybe check your neighbor of how they did it. Maybe I'll write a couple of little hint things on here while we're doing a 1-minute timer. Go. How are you guys doing here? So if I had a chapter 10 portion of my aid sheet, these are some things I would put on there. The simple harmonic motion equation, x equals a times cosine of some constant times t. And I'd also put on these two equations, either which works, for the total mechanical energy of a mass on a spring. Go once, go twice. Do I know the answer? I think I do. And stop. Oops. Keep doing this. Stop. 63% of you are voting for 12 joules. Let's see what I get here. So what's A? You just sort of compare this equation to this equation, and I would say that compare shows you that A is equal to 0.35. And doesn't really say it anywhere, but I think it must be meters. Well, actually it does say. It says the ball's position in meters, so there you go. And then, so which of these, we don't know Vmax, we do know A, so we can just use that. So we'll just use E is equal to 1/2 Ka squared. So it's E is equal to 0.5 times 200 times 0.35 squared. So let's do that on my calculator. 0.5 times 200 times 12.25. So I like to eat as well. So good. Okay, I also didn't derive the pendulum last time, so we want to do it. Pendulum is a weird thing because it's actually, if you think of it, it's circular motion. Because wherever that string is attached is like the center, and you could go technically all around in a circle, but no matter where you are, you're on a circular path. So to properly do this, I think we should use torques. I'm not ready for the real demo yet, but a couple minutes. What is the net torque on this pendulum? Assume the rotation axis is the point where the string is attached to the ceiling. So I'm going to label this as the axis of rotation, and I can find torques around there. It's only, well, actually, tension is just towards the thing. So here's tension of the string on the mass, and here is mg, right? So the torque from the tension is 0 because no matter where it is, the lever arm of the tension is going to be 0 because the force line is going to go straight up the string to the rotation axis. So there's no distance between the force line and the rotation axis, so it means tension doesn't torque this thing. So it's only coming from gravity, since the force line of tension, I think, always passes through the rotation axis. Through the axis. Make sense? And then, so now we need to do the work, which is, let me draw it here. Here's mg, here's the line, here is that string of some length, here is the rotation axis. So this is the distance, I'm going to call it x sub g. The torque due to gravity is equal to mg times x sub g. This is, at least the absolute value is, force times lever arm. Do you remember how we do all that? And then if this angle by the z rule, if that's theta, then that's theta. And so I think it's just x sub g is equal to, isn't it L times cos theta or something like that? No, sorry, wrong. Sine theta. Let's do it properly. This is a right triangle, so the sine of theta is equal to that lever arm divided by L, the hypotenuse, which is the string length. So x sub g is equal to L sine theta. So what we're going to have is the sum of all the torques, which is equal to I times alpha. The sum of all the torques is equal to just the mg L sine theta. The question is it negative or positive? If gravity is the only force, it's a little hard to see it, but I think it would turn it in this direction clockwise. So it's a negative. Does that make sense? I'll put it in green here. It's kind of a clockwise torque. That's why I put a negative sign. Are we good with that so far? How I found those torques? So then I'm going to just plug in here and solve it out. I've got some of the torques, xi times alpha is negative mgl. Yes. This is where we do a trick, which is we do what's called a small angle approximation. So you remember how we had sine theta? I'm just going to call it theta. I don't know how you guys feel about that, but that's what's called in physics the small angle approximation. Comes in handy. It works when you have theta measured in radians. You could try it on your calculator, set your calculator radians mode, and do the sine of 0.01 or something like that. You'll get 0.01. It's always the same. Even 0.1, I think, is pretty close. So when you do that, now we have this just theta. So you get alpha, which is an acceleration of theta, equals negative some constant times theta. So this is like ding, ding, ding. That's the simple harmonic motion equation. Whenever you have the acceleration equals negative a constant times like x, like the thing that's actually moving, that's got this solution, trial solution.
Pardon me, Professor,
Yes,
there's a question.
Do.
How do we find energy in a pendulum?
Same exact way, I guess. I would use the 1/2 mv squared when it hits its minimum. It's got some, I guess what's happening here is that instead of a spring potential energy, you've got gravitational potential energy. Right, so you can use mgh, or you can use 1/2 mv squared.
There are 2 more questions.
Please.
Can we explain why it's negative because it's clockwise again?
Yeah. So what's happening here is that theta is positive, it's counterclockwise. And so what you have is that you've got gravity is a restoring torque, if that makes any sense. So that it's negative or counterclockwise if theta is counterclockwise, and if theta is negative, then I guess the torque will be positive. It's always bringing it back towards theta equals 0. That's a really good question. And third one?
Can you please explain how to get the proper angle between the lever arm and the force line?
Well, that was that right angle triangle, wasn't it? I just drew a triangle right here. It's just a geometry thing. So that's the great thing about torques, is I just like to, first I know the force, and then I multiply it times the distance, the actual physical distance in meters, between the line that goes through the force, which you just extended out up and down for gravity here, and the rotation axis. And it's always a perpendicular distance. Lever arm is always perpendicular to the force line, and then it goes through the rotation axis. Hopefully that answers those. Where are we here? We're on this. I told you that this is simple harmonic motion, and the period is this. So, that doesn't look right. Oh, yeah. So, if it's a massless string, then I would say that this I is equal to m times L squared, right? So then you plug that in, and that's when you get the m's cancel, and the l's, or one of these l's cancels. Anyway, you end up with just L over G, I think. What time is it? Well, yeah, why don't I let's do the demo and then we'll do a bunch of learning analytics. So, thank you, Bias. There's 2 demos today. But this is the first one. We already sort of did this, is that this is a 200-gram mass and a 100-gram mass, and they're both at the same length pendulum. It turns out mass does not affect the period. But a 200-gram and a 200-gram on different length pendula, you have a longer period for the longer L. Okay? So then we have masses on springs. Let's take these down for a sec. We have 2 identical springs. So if I take 2 masses, like the 100-gram mass and the 100-gram mass, and I hang them, well, turn it like that maybe. Okay. I guess we could move this down, right, out of the way. It's easier to see, yeah. So what I do, they're sitting in equilibrium. I pull them down below equilibrium, release them, and they oscillate together, pretty much. Same K, same M. If I increase the mass and do a 200-gram, first of all, it's at a different equilibrium. But what about their periods? If I take them and release them, Okay, so now we have a longer period for the higher mass. So that's the 2 pi square root m over k, I think, right? So higher mass, you get a longer period. And then I've got another spring, so let's compare with this spring. So I have another 100 gram mass. I can put it on this spring, and whoa. Okay, so that's a low spring constant. When the spring constant is a low value of newtons per meter, it goes a long way, even for 100 gram. Can I hang the 200 gram mass on there? It won't break it. I'm always afraid of destroying your springs. If I hang the 200 mass on here, oh my God, it goes. Okay, so, well, you got it. Hey, why don't we do that? We'll put the 200, so same mass on both springs. You take them a little below, find its equilibrium, below equilibrium, release it. Oh, you can't even see it. It's going, well, it's below my video. Let's do 100 grams. So its period is square root of 2 pi times the square root of m over k, right? So if k is larger, you should have a smaller period. So, yeah, that's on the denominator has a much smaller period than this one. Okay, so I think those are those. Thank you. All right. And in the meantime, I've got 3 learning catalytic questions for you. Question 1. First of 2, 3, and 4. 2 pendula had the same length, but different mass. So the one, the larger mass, maybe the 200 grams, has twice the force of gravity as the 100 gram, right? Because F equals mg. So which one has the longer period? Give you a minute to think about that.
Professor?
Yes.
What counts as a small angle to make the small angle approximation?
Yeah, that's a good question. It depends how precise you want to be, right? So my rule of thumb is about 10 degrees. It's a small angle. Because then your mistake or your error in using small angle approximation is less than like 1%. And so you can use 2 significant figures. It's a great question. Rule of thumb, let's just pick around 10 degrees. All right. Yeah, we're done with all those ones. How are you guys doing? 15 seconds to click an answer for this one. How many? I see 250 responses. I don't know how many people are in this room. Okay, that's your time. Go once, go twice, and stop. Survey says, ooh, a lot of you are saying neither, which I totally agree with. It doesn't have anything to do with the mass. Don't forget that assuming that they have the same length, which they do, then the period is 2 pi square root L over G. Okay, you got it? Let's do this next one. The little girl on the swing. It's saying, so someone first sits properly on the swing, and there is some natural period of oscillation. And then the person stands on the swing. The new period of oscillations, is it greater, the same, or smaller? Please discuss. If you have a neighbor, I'll give you a minute to discuss. Can we remove it? Because we got the video in front, right? 10 seconds-ish. Okay. Go once. Go twice. Survey says. A lot of you saying that smaller period, 65% of you, and it's colored green, which means that I thought that too for some reason. Why did I think that? Smaller L. Yeah. It's because the center of mass, the distance between the center of mass and the rotation axis is roughly L, right? So this is a tricky one. But can you imagine, it's sort of like if you're sitting, it's a little hard to draw this properly. There's a person, then you kind of think of the center of mass as maybe here, and so then the distance L is this distance. This doesn't look very good. Anyway, if you had then the person standing, I think what that kind of does is move that center of mass up. So the effective length is longer, I think, or is shorter. So effective length is less. And again, its period is equal to 2 pi square root of L over G. So if L goes down, I think the period should go down as well. That's what I was trying to get at there. And what I told you there's going to be one more, right? Oops, right. There it is. Grandfather clock. So calibrated at sea level is now operating in Calgary, which is 1 kilometer above sea level. This clock runs A fast, B slow, C normally as it does at sea level. Think about that, and I'll give you 1 minute to discuss. So we're totally done with that. Okay, you guys got an answer for me? Give you 10 seconds to click this in. Remember, you get 0.8 points just for clicking anything in, which is quite a lot since we're all held at a maximum of 2/3 anyways. Go once, going twice, and stop. Survey says 59% of you are voting that the clock runs slow in Calgary. And I think that's correct. So, meaning that you're 1 kilometer above sea level, you're farther from the center of Earth. So, gravity is less. So, instead of G is 9.8, a bit less. It's going to be 9.79 or something like that. So and that might matter, right? If you've got a clock that's ticking for months or something like that, you might find, hey, look, this clock is kind of running slow because it's losing a little bit of time every. So it's slight increase in T. T is the time between like ticks, right? So instead of like normally, you've got tick, 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 right? Now the time between ticks is now, or Calgary, tick, 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 right? That's a longer period. That's called your clock running slow. And I think it's going to make you late. Or, yeah. So when it's really, the rest of the world, it's 10 a.m., your clock says 9 a.m. and you keep sleeping. So it's bad. So, okay, slow clock. When you walk, your arms and legs swing back and forth. These motions repeat themselves. So this is mentioned in the textbook as being kind of a model of walking. If you model your leg as sort of a pendulum, which it sort of feels like if you just sort of let your legs swing back and forth. Your leg can be modeled as a simple pendulum with the length equal to the distance between your hip joint, which is the rotation axis, and the center of mass. So you can even, if you estimate that as 0.5 meters, you can go through and get 0.7 hertz as being a kind of a rough sort of frequency. So by the way, frequency is 1/period, so I've just turned this equation upside down. But the basic idea, longer legs have lower swinging frequencies. So giraffes take fewer steps per second than humans because of their long legs. You'll watch them kind of lumber along. Whereas little doggies, you'll see their feet go really, really quickly because they just have a shorter length. Once again, I think it's better to do, I'm not going to do this example right now, nor am I going to do that. I have some time, so I'm going to go on to damping and driven simple harmonic motion. So what we've been doing up until now is just assuming that the oscillations go on forever. So another way of putting it is that cosine is forever. So if I model the position, x equals a times cosine of this thingy times t can range from -infinity to +infinity. We kind of got this idea that this thing's always going to oscillate and always has been oscillating. So it can't really work in real life because nothing oscillates forever, right? So there's maybe friction or drag, things will slow down. So there's a phenomenon called damping, which is it could oscillate with some amplitude, but the amplitude can decrease with time. So that back in that equation, x equals a times cosine of something, you still got the cosine, but now you've got a decreasing amplitude. So, and it's a useful aspect of the design of vehicles and bridges. So things that oscillate, you don't want them to bounce too much, but you want them to bounce a little. So if you have the same mass and the same spring, but it's in a different kind of fluid, you can get different amounts of damping. So, example, if you have a mass hanging in air and you pull it down, release it, or I guess I could bring it up and release it, its position will look like this. It'll oscillate with cosine, but very gradually the amplitude will decrease. So at some moment here, it's A. At some moment later, it's less. This is like A0 and A at some time, A1 or something like that. So A decreases with time. However, if you put the same mass in water, you can see that now the amplitude decreases faster because water's thicker than air, so there'll be more of a friction force there. If you put it in honey, you might pull it up and it just never even oscillates at all. It just kind of, the spring gradually pushes it, but it doesn't cross that equilibrium. And there might be some other viscosity fluid where it kind of goes down and just hits its equilibrium again. So this is called the 3 cases of damping. There's called a weakly damped system, which is where it vibrates for many periods. An over-damped system in which the vibration takes a really long time or never returns to the equilibrium position. And then there's something called a critically damped system, in which the vibrating object returns to equilibrium in the shortest amount of time possible. But it doesn't vibrate. So it's sort of just an interesting thing. We could talk a little bit about energy, I guess. It is energy that's going away. So let me give you a quick question here. A 0.5 kilogram cart is attached to a horizontal spring, the other end of which is attached to a fixed bumper, like the wall or something like that. The spring constant is K is equal to 150 newtons per meter. This is K. And the cart is pulled to the side and released from rest when the spring has been stretched by 0.035 meters. So that is going to be the initial amplitude. Okay, something like that. How much mechanical energy is converted to internal energy before the cart stops oscillating? So we're looking for a number of joules here. I'll give you a minute to think about that and share with your neighbor. Make sure your neighbor can help you get that extra 0.2 points from these. Or you can help your neighbor. It's probably a good idea to bring your calculator to these classes, eh? Yep. Yeah, so really, I think it's not really the amplitude, I guess, because it's not necessarily simple harmonic motion, but it is the maximum displacement from equilibrium. The reason I wanted to do that is because I wanted to use this equation, equals 1/2 K A squared, because it was on my aid sheet. That's why I put that as A. But it's really X, I guess. Okay, guys good? Going once? Going twice? Stop. Survey says we had 259 responses, 79% voted for 0.09 joules. So, like I say, to me, like I'm not a student, so I am using the calculator on my my iPhone, but I think I would just be carrying my calculator everywhere with me, because you want to get used to using the calculator you have to use on the final exam, I think. Be my recommendation. You don't want to be like, hey, where's the squared button on this crazy calculator in the middle of a midterm or final exam? I got 0.0918, whatever. Anyway, it's A. Because I'm using newtons per meter and meters squared, so I've got SI units, so I know the whole thing's in joules. SI unit of energy. Okay, so let me tell you where we're going with this. We did a whole bunch of simple harmonic motion, which just lasts forever. Now we just finished doing damped harmonic motion, which means that there's some friction. So now we're going to do kind of the opposite, which is driven harmonic motion. So what you do here is you consider a system for which, when it's left to itself, it oscillates at some natural frequency. So if we think of being on a swing, like remember the kid on the swing, sitting properly on the swing, you're going to oscillate with some period, or another way of saying another certain frequency, I guess, which would be F0 now. That's the natural frequency. But now you have a parental unit of some kind pushing you on the swing. And this is an external driving force. And the idea is that the parent doesn't just push you like with a constant force. The parent will push you with a force which has its own frequency, actually, a repeating force. And the way it goes is you don't just hit the kid with a high frequency, or you don't hit the kid with a low frequency. What you do is you match the driving frequency to the natural frequency, and then you get resonance, where the kid just goes higher and higher and higher. That's called what's called resonance phenomena. Resonance is when you have a natural frequency F0 and a driving frequency F external, and F external is close to F0. And in fact, if you look at the amplitude as a function of your driving frequency, then that amplitude goes up and has a peak right at F0, the natural frequency, called the resonance peak. And so remember what F0 is? It's this is the simple harmonic motion frequency that you can find from that equation. It's F0 is 1 over T0. It's going to be 2 pi times the square root of m over k, something like that. Times it. Yeah, we're good. And then there's this thing in the textbook, which is, I don't know if you've seen it. You have the leftmost ball. I had some students asking me what the heck is going on in this diagram. Let me try to explain it. The leftmost ball represents an external driving force. So what happens is that someone sets the 80 centimeter length ball swinging back and forth because somebody pushes it. The question is, what happens to all the rest of them? Well, what will happen is that the 10 centimeter will maybe kind of move around a little. The 50 centimeter will move around a little bit. The 100 centimeter will move around a little bit, and the 140 centimeter. But what will happen is the ball 3 will just start going really, really fast. Because, so ball 3 is at resonance, because its natural frequency is the same as the driving frequency is at resonance. So oscillates or vibrates with a large amplitude. And I have a demo kindly set up by Pius that's going to try to demonstrate that. It's a bunch of sawtooths. It's probably easiest to see if you're actually in the front row like you people, but there's also a video, but can you kind of see it in the video? There's these little, it almost doesn't show up much, but there's saw blades of different lengths. And so the longest saw blade has a low frequency, and the shorter saw blade has a higher frequency. And then what I can do is turn the crank. And what the crank does is it oscillates the whole system back and forth at some frequency. So what I'm going to do is increase the frequency bit by bit and see what happens. Because when I get to the frequency of that longest saw blade, then it should set it oscillating. I match the natural, there we go. Whoop. So that's the natural frequency about of the saw blade, the longest one. And now if I keep increasing the frequency, a little bit by bit, I go to the second longest saw blade, starts at high amplitude, then the third longest saw blade, and then the fourth. I just keep going up the until I get to the longest or the shortest one. So when you hit a saw blade resonance frequency, that's when it has a very high amplitude. There, that's the highest one. So just sort of showing what I'm doing. It's the same thing you actually do on a radio. You tune your natural oscillator to match some driving frequency. So the driving frequency would be like the radio station coming along at 92.5 megahertz or something like that. If you're listening to KISS, then what you do is you set your dial to resonate at that frequency, and that's when you'll hear the music from that particular driving frequency. So I'll do that next time. This can also happen in real life with bridges. So there's what this did is in the Tacoma Narrows Bridge, there were these gusts of wind coming at a particular frequency, and they designed a suspension bridge which had an oscillation frequency exactly at the gusts of wind, and so it ended up destroying that bridge. So that's energy transfer through resonance. And what we're going to do next week, I'll do a couple more examples just from Chapter 10, and we'll get into Chapter 11 on waves. And I'd like you to answer which of your 5 senses actually depends on mechanical waves. And I'll see you Wednesday. And thank you so much, David.